All right. I'm Aaron Moss, and this is Adedigio Dewoe. We are working on space situational awareness. We're protecting objects in geosynchronous orbit. The problem is, let's see, how does this work? Right button? Like that? No? Let's see.
Oh, you
No.
pointed at the projector.
At the projector?
That's what we did.
Did it get turned off?
There's a button on the left side. Switch on the left side.
Can we edit
No.
that?
Oh, that's a shame.
I'll just
You'll hit that? All right. Ready to go? All right, so sorry about that. Technical difficulties. So the problem is in orbit, we have a picture, and you can see that space is getting more and more crowded, especially in the geosynchronous orbit area, which is where all our communication satellites are, all sorts of really important that provide services that we rely on. And collisions are becoming more and more likely because it's getting so crowded. And so we are working to track these objects. Next. So we have two goals. The first goal is to track all the satellites. And we're going to track satellites that are functioning and debris. And among the functioning satellites, we have ones that are cooperative, which means that they will let us know their data, and ones that are non-cooperative, satellites that don't update their position with the space catalog or anything like that. They kind of hide their actions there, incognito, I guess. But after we track our satellites, our next goal is to issue collision alerts. And so we are developing a method to determine the collision probability and issue collision alerts based on that. And so, for example, if two satellites were to approach within 6 kilometers with a probability of 20%, we would issue alert and say, you need to pay attention and see what's going on and analyze the situation and see if you need to make a maneuver to avoid a possible collision. Next slide. The difficulties and the first step of tracking the satellites are that the orbits are always changing, whether they're intentional changes such as station keeping, just adjusting your orbit to not decay or anything like that, or whether you're specifically changing your orbit, transferring to new orbit. Those are changes that we have to watch out for. And as I said, we might either be informed or not informed, so we have to track satellites continuously to determine. Unintentional orbital changes, the orbits are always, they're decaying, they're changing, and there are a couple of factors that influence that. For instance, there's the anomalous gravity of the Earth. Since the Earth isn't a perfect sphere and some areas are denser than others, satellites don't orbit perfectly as we would hope from Kepler's laws. There are torques from the gravities of the sun and the moon as well. And there's also solar radiation, so the light hitting the spacecraft actually puts some sort of thrust on it and it changes position. Next slide. So our solution to account for the uncertainty is to use an unscented Kalman filter. We will provide the Kalman filter with the current state, and it's going to be expressed in the Cartesian coordinates, x, y, z for position x, y, z for velocity. The Kalman filter will propagate the orbit until the next state is passed in, at which it will correct itself and keep propagating further and further. It works on prediction, measure, correct technique. We get our data from the Air Force Space Command. They keep a space object catalog. They provide data for thousands of objects, and they update the database every couple minutes. I don't know exactly, this is something I do want to find out, how often they update an individual satellite. But I know they update the database every couple minutes. It's given in the format of 2-line elements, which is Keplerian orbital parameters. We need to convert those to our Cartesian coordinates, and that's one of the things we're working on. The 2-line elements to Cartesian coordinates. We take the orbital inclination, the right ascension of the ascending node, eccentricity, argument of perigee, element set epoch, and the mean motion. With that data, we can convert them to the Cartesian coordinates. We have MATLAB code that we've been working on to do this, and that's just the beginning step of our project. So we take that data and we convert it to Cartesian format, and then we can pass the vectors into the unscented Kalman filter. We have code to work with that we've been given a basis from which to start. So next slide. So our procedure, after getting the data, we pass it into our unscented Kalman filter to propagate the orbit. And here's an example unscented Kalman filter. And so we have in this example, we have a tracking satellite and then the satellite that we're tracking. And so we have a target and a prey, for instance. And as you can see, we have the 6 Cartesian coordinates. The first 3 are position x, y, z, and the second 3 are velocity x, y, z. So we start with a position and velocity known, and we pass and we generate a trajectory. And that goes into the Kalman filter. It gets updated with the true states, and then we propagate the orbit and update it as we get more true states coming in. And so at this point, I'm passing it on to Adediji to talk about our probabilistic method for determining collision.
Like Aaron just said, we're tracking various satellites with a particular a satellite in geosynchronous orbit, and the Earth is in the way. So that brings us to the fundamental problem that if we're tracking satellites with satellites that are revolving around the Earth, there's going to be a time when the Earth, as big as it is going to be in the way of the tracking satellite as to measuring the positions of the satellites we're tracking. And that brings us to the point where we can't know for certain where the targets are if the Earth is in the way. So we have to develop a probabilistic model that answers the question of where would this satellite be in the next few minutes that we're not measuring in it, and what is the probability that this satellite is going to be in the same region as a satellite Y that we're not measuring at the same time, and what's the probability that they will collide with each other. Now, like the slide measures here, like the scenario I was just painting, there's a satellite in the LEO and tracks one satellite. When the tracking satellite passes behind the Earth, there is go to the next slide. There's a problem. This is one satellite in the geo orbit, and there's a low in the lower orbit. That's this tracker which we named the observer. And say the Earth is right here, the tracking satellite is right here. We can't see it. So this red marks the region of uncertainty of this satellite. It could be anywhere between this region. That's what we're working on right now. And if there's another satellite, say another geo satellite, Geo2, whatever, is over here, what is the probability that they would collide or be in the same region, in the same red region, if we can update our measurements by the tracker. You go to the next slide. Now the question I'm trying to answer, because I'm obviously an EE and Aaron is not, is the PDF, the joint probability density function of these satellites. Like, for example, we know we can propagate the trajectory of the satellites. If we're given the motion, we can use the EK on the unscented Kalman filter to get the trajectory. But the question we will be asking Dr. Chen next is, how do we actually get the functions? If we have all these data, and we have the trajectory that's been projected, but we don't have the joint probability density function. If we don't have that, we can't get the error function to calculate the probability of them being in the same spot at the same time. And yeah, I don't want to talk too much. It's gonna be the repetition of the same thing. But we have this. Like I just said, if we know the joint PDF for both satellites, we can get the probability of them colliding if they are not being tracked by the LEO satellite. Next slide. Yeah, based on our probabilistic model for the satellite trajectories, collision alerts will be issued, like Aaron said, if the satellites are within, for example, 15 kilometers between each other and have a tendency of 20%, which is a probability of 0.2 of colliding. A collision warning will be issued if the two satellites will be same thing. This criteria are yet to be determined. Like I just said, we don't know the joint PDFs of both satellites, and that's what we'll be working on. Last slide. Yeah. We're going to be verifying the data we use. For example, I was working on Dr. Chen gave us a task to design a code that can convert from two-line elements to the Cartesian coordinates. I was just putting random values, and it was giving me all sorts of values. So, but I don't know that those values are actual values that will work for a satellite. So we're going to be verifying our satellite tracking abilities and the values that we're using with standard values from the Air Force. We're going to judge the performance of what we design against a metric, the standard metric, since Dr. Chen knows what should be available, what our results should be like. And another thing we're interested in doing is expanding from, for example, I just talked about one LEO satellite tracking 2 GEO satellites. If it's possible for us to generalize the system whereby we tracking more than 2 GEO satellites, we say more than 1 LEO satellite, we have data coming from radar, measuring from a stationary point on the Earth, multiple trackers, multiple satellites, in the short sense of it. Next slide. What we're doing right now is what, for example, we all watch TV, we've seen the commercial where the Air Force says there's somebody in the Air Force room and says whatever, the satellite's about to collide and says launch and maneuver, I don't remember the exact word, maneuver avoidance or something like that, and then the satellite moves and then it said collision avoidance, something like that. That's what we're going to. We're trying to avoid collision of things that are important to us, like the GPS system and all the satellites, national defense, and stuff like that. I get lost a lot, so I use my GPS a lot. So that's where, that's where we apply what we're using right now. And go to the next slide. Yeah, and our sources, in a nutshell. And thanks to Honorable Dr. Chen for his mentorship, Dr. Dimitris and Dr. B. and Dr. I said and the NSF, National Science Foundation, for funding us. That's pretty much it.
That's it. Any questions?
A question. It's not clear to me why you chose to work on Cartesian coordinates, as opposed to say spherical, which seems more appropriate to me, given the geometry of your problem.
I agree that spherical does seem to make more intuitive sense. We're working with the Cartesian coordinates because that's the example code that we have so far that we're working off of. It takes in the arguments, and as a starting point, that's what we were given. And so that's why we're following through with the Cartesian. Mm-hmm. Any other questions? Dr. Demetrius?
I'm thinking how to phrase it. Anybody else?
I have another one.
Okay.
Tell me again what your reference is, what you're measuring with respect to.
Oh, our reference would be the Earth, so the center of the Earth.
So the center of the Earth, so
Mhm.
that's fixed.
Yes.
It's a non-moving
Well,
reference.
yes.
Well,
Not
Well,
really.
no, it's not rotating, but it's moving.
Yeah.
Yeah.
Okay.
Oh, that's good.
So, for instance, our X would point at the sun. Our Y is, of course, perpendicular to that. And no, mistaken.
Oh, I think it's called Earth-centered inertial coordinate system. That's the,
Oh, okay.
that's the reference.
Yeah, the satellites are moving with the Earth, so we focus about the center. It's like me rotating the Y-Z axis. The center, the origin is still the same thing. It's still 0, 0, 0.
But there's some uncertainty on that exact location also, right?
Yeah, yes. That's going into the nitty-gritty of it.
The grid is fixed. So our X or our Y would point from the center of the Earth to the sun, and then the other, and then you can determine the rest by the right-hand rule.
Right. So are you assuming that you have certainty on that reference?
To the level of difficulty of the questions, yes.
Yes.
Yes. If I understand what you're saying the center of the Earth.
Mm-hmm.
Yeah. No. To the difficulty of the question.
So
yes,
you're not accounting for that uncertainty.
Making that basic assumption. That assumption shouldn't be. That shouldn't affect the readings that much. It's not going to be that huge. I don't think so. In the hundreds of kilometers. If you can get there, then we're in trouble.
Yeah.
Okay.
So the final, let's say, result would be the probability of collision between two objects, more than two, and or is it also probability of existence, let's say, of two objects within the same region?
Yes, that would be the final project, or the final product. It would be if we have two that are getting close to know the probability that they will at a certain time be within a certain distance.
Okay.
Yes. Any other questions?
Michael is smiling.
All right, well, thank y'all so much.
All right, thank you.